Okay, good morning. Thank you, organizers, for this exciting session and a look at sedimentary geology in the future. Before I begin, I would just like to acknowledge the great group of scientists that I get to work with at MIT, as well as a range of collaborators through the years who have helped inform my thinking. I'd also like to acknowledge all of the funding sources that makes this science possible. The Precambrian Phanerozoic transition is arguably the most significant change in carbonate rocks over all of Earth's history. And yet traditionally, researchers tend to not cross this boundary at 541 million years ago. Geologists tend to work up to the Precambrian boundary or down to the Precambrian boundary, generating sedimentological catalogs and geochemical records. And yet that strategy has left very large unanswered questions. For example, what the climate history was like before macroscopic animals evolved in the fossil record. This advent of biomineralization is also a critical dividing line for our geochemical proxy records. This is in part because biominerals are large and charismatic, and they're easy to sample independent of their matrix. They form predictable physical structures that can be evaluated at the micron scale for evidence of alteration. So they're ideal geochemical targets. Over on the right, you can see this in high resolution, 2-micron scale bar, from a synchrotron-based crystal orientation mapping approach, where the aragonite nacre tablets of bivalves are well systematically oriented in the top map. And in the bottom map from a Jurassic bivalve, we see dissolution of aragonite tablets, the replacement of aragonite with a calcite, and the suturing of these nacre tablets. When we cross the boundary into the Precambrian, we're limited to carbonate rocks of many types, and these rocks often have few primary predictable structures. And so we're left sampling and analyzing the sum total of a series of events. And these could include everything from the initial precipitation out of seawater, the dissolution of unstable carbonate phases, the dolomitization of a sample. And so looking at these rocks, you can understand why the Precambrian is a critical dividing line for geochemical efforts and why most sedimentologists have run away from it. That said, I think that there's hope, because the timing and number of different events that we must contend with varies dramatically by facies, lithology, the depositional environment, and burial history. And so the approach that I've developed for the Precambrian is to target locations with minimal burial history and tectonic deformation, and to assess the spatial patterns of physical and chemical trends using microanalytical techniques, and appreciate that all rocks are at best altered sediments from their original muds and grains, and the only diagenetic event that we might have to contend with is cementation and early lithification. And rocks like this fenestral mudstone from the Ediacaran of Oman give me hope, because what you can see is that the original fenestrae forming in a peritidal environment are still open. They're not occluded with a later pore-filling cement, and the original mud is now a micrite of very fine crystal size. Even more hope, some Precambrian carbonates form predictable physical structures that can be evaluated at the micron scale for evidence of alteration, like these ooids, where we have crystal orientation maps of the radial growth structure. So why would we want to go through this trouble of trying to see through the ravages of time? To me, the question really boils down to the fact that climate changes could have helped drive the larvagist revolution in the history of life and the timing and tempo of ocean oxygenation. We also have physical evidence for major climate swings. So this is a drone map from Svalbard of glacial diamictites capped by warm water carbonates with unusual sedimentary structures like these giant wave ripples with a hammer for scale. And models of how to achieve this dramatic juxtaposition of lithologies have anywhere from temperatures predicted of minus 35 degrees C to over 50 degrees C for the carbonates overlying the diamictites. So I asked the question, how can we do a better job reconstructing Earth's temperature history? Traditionally, since Harold Urey first proposed the Delta 018 paleothermometer, we've had a problem where the Delta 018 of a mineral that you might measure in the lab is a contour in temperature Delta 018 water space. And so we cannot actually distinguish the range of temperatures and fluid compositions that a Delta 018 mineral composition might reflect. And yet, there are very striking patterns if you look at the Delta 018 of many different minerals through time. So the calcite, dolomite, apatite, chert, various iron oxides all show a change to more enriched values in the modern. This has led to two end-member interpretations that have divided scientists for over 40 years. And these predictions can really be boiled down to a well-buffered climate system that has kept us within degrees of the present temperature, apart from significant glaciations. And in this model, the seawater Delta 018 composition of the ocean evolved over time. And that can be contrasted with the model of a well-buffered Delta 018 of seawater composition and of an evolving climate through time. I look at this record with its 30 per mil spread in Delta 018 from a given time bin, and I think it's inadequate to answer this question. So one thing that I've set out to do is cross the boundary. And I've done this by generating a high-resolution Delta 018 record that's time-resolved with an age model. It's screened for burial and diagenesis and significant tectonic overprint. We include fabric-retentive dolomite from the Precambrian, and we're working to include both fossils and rocks from the Phanerozoic. It's a work in progress. This is a big task. But if you look at this record, we can see the general decline as you go towards the Precambrian Phanerozoic boundary, and then significant structure and yet variability in the Precambrian. So we can do the same thing that these two sides of the debate have done and assume either a well-buffered Delta 018 seawater composition and take an ice-free estimate and calculate the expected temperature, or take an assumed well-buffered climate system, take an equatorial temperature of 25 degrees C, and calculate the expected Delta 018 of seawater. And so we end up with these two end-member models as time series that we can evaluate. So in the top panel, we have the prediction for a well-buffered climate state with an evolution of seawater Delta 018 down to values of -6, -7 per mil. And in the bottom panel, we have the prediction for a constant, well-buffered seawater Delta 018 and evolving climate where you can see temperatures increasing back in time. So how do we deconvolve these two parameters? So we are pairing the original Delta 018 paleothermometer equation, this equilibrium exchange reaction with water and carbonates, with a second equilibrium exchange reaction that is just within the carbonate system, where we're looking at the abundance of two heavy isotopes within the carbonate molecule. And so now, with these two paired equations, We have a measurement of temperature from the clumping of the two heavy isotopes. We have a measure of the delta O18 of the mineral, and we can use the two to calculate the delta O18 of the water composition. In practice, this is what it looks like in the lab, and we dissolve about 400 micrograms of carbonate, produce CO2 gas, and then separate it between different signal collectors. Importantly, the abundance of these clumped CO2 molecules are rare in the entire CO2 sample. Okay, at this point, we have worked to create a record that spans the Precambrian to Phanerozoic in a range of fossil types, mineralogies, and rocks. It's global. A lot of the sections are flat-lying. The best sections, when you visit them in the rain, have carbonate mud that still sticks to your boots. And this is the sum total of the results. So what I'd like to draw your attention to first is this upper panel, where we have the delta O18 of the fluid from our clumped isotope measurements, and this is everything from aragonite fossils, apatite fossils, calcite rocks, dolomite rocks through time. And importantly, none of the delta O18 fluid compositions fall below this dashed line of minus 1.4 per mil, which is the expected recent seawater composition for ice-free conditions. Particularly in the Precambrian, we're nowhere near the predicted minus 7, minus 6, minus 8 per mil delta O18 seawater compositions. In contrast, we do see a general increase in our clumped isotope temperatures as we go further back in time, but we also have variability in the record. Taking a population approach from the Precambrian data in particular, you can see that the minimum clumped isotope temperatures that we are recovering from, say, the best preserved carbonates from a given time interval do not yield significantly different temperatures to today. So the Syn glacial carbonates are between 15 and 20 degrees at the low end. Interglacial temperatures, 33 to 37 degrees C at the minimum. And so this suggests a best estimate that we can start with of a minimum clumped isotope temperature estimate and a minimum delta O18 estimate from a predicted constant seawater delta O18. And so the red line is that, and the stars are our minimum clumped isotope temperatures. And so you can see that this temperature range reaches about 40 degrees C at the Precambrian-Cambrian boundary and is variable through the Neoproterozoic with a few periods that suggest we should think about even warmer temperatures. So the first results, we're finding evidence for near constant minimum seawater delta O18 compositions based on over 300 samples and more than 2,000 replicates that are paired with thin sections of 4 different minerals throughout the record. We're finding that the Precambrian climate was warmer with extremes, both hot and cold periods. And currently, our minimum temperatures from the glacial intervals are colder than their surrounding rocks, but have yet to reach those modeled negative 35 degrees C snowball temperatures. So the implications of this are we might need a new model for Earth's long-term climate to understand the Precambrian versus Phanerozoic climate states. So this has me returning to a classic model by Walker, Hayes, and Cantine from 1981 to think about what sets Earth's climate over long time periods. And so in this model, we have CO2 from volcanic outgassing taken up by silicate weathering and stored and sequestered in carbonate rocks before being returned to the mantle. And this cycle is thought to keep global temperatures within degrees of the present. And yet, I think it's important, we'll go back. Much of my thinking has actually focused on this third leg of the pyramid. And in particular, I think it's important to ask questions like the flux of carbonate to the seafloor through time, the size of the carbonate rock reservoir through time, and what the return flux to the solid earth was through time. Today, CO2 is efficiently sequestered into carbonate sediments through planktonic calcifying organisms. It's responsive, and we have a significant amount of carbonate on seafloor crust that can then be easily subducted at subduction zones. Planktonic calcifying organisms actually overproduce carbonate, and only a third of their carbonate makes it to the seafloor. We also have about 60 million gigatons of carbon stored in carbonate rocks and sediments today. And I think the question of when and where this sedimentary carbonate reservoir was built is critical. This is an incredibly large reservoir. Currently, the amount is similar to the volume of CO2 in Venus's atmosphere, which keeps it at 465 degrees C on average. And to tackle that question, often in the literature, you find the assumption of geochemical uniformitarianism, that the total mass of sediments of all ages that existed at a given time may have been about the same ratios of rock types that we observe today. And a corollary is that the fluxes of chemical constituents to the oceans have not varied greatly. I will say that trying to answer this question is not easy. It's fraught because the rock record is constantly being weathered and eroded away. But I think the proportional comparisons of rock types through time should be informative for answering this question. And so the first effort to do this was Soviet scientist Alexander Ronov, and this is his Phanerozoic record coupled to his later published Precambrian records of estimates of the percent of carbonate rocks compared to the total sedimentary rocks per time bin. And you can see that Precambrian rocks make up something like 10% of all sedimentary rocks in the Precambrian, where the mean in the Phanerozoic is more than 20%. Another estimate is from the geochemical database EarthChem, again imperfect. This is the percentage of carbonate analyses versus all sedimentary analyses, and you can see a significant change across the Precambrian-Cambrian boundary. And lastly, a higher resolution estimate from Macrostrat, which is a North America-based estimate of rock types, has the percent of carbonate versus total sedimentary rocks as significantly changing again across this boundary. So while all of these are imperfect, they all suggest we should really look at this time interval for a period when we're changing the sedimentary carbonate rock reservoir. So what was going on? Well, biomineralization was evolving, and biomineralizing organisms do their carbonate chemistry internally within membranes, and the rates of carbonate precipitation can outpace abiotic precipitation by more than 200 times. And they use all kinds of phenomenal pathways to do this. They use proton pumping, enzymes like carbonic anhydrase, and they overcome kinetic inhibition to boost their supersaturation within their tissues. And so I think it's worth asking then, are we seeing this transition where the total volume of CO2 sequestered in carbonate platforms changed? So the Phanerozoic carbonate platform model becomes one of aggradation to sea level and significant progradation as you overproduce carbonate sediments in these shallow environments. Whereas the Precambrian carbonate platform, while it still aggrades to sea level, is not as large. Progradation is not as significant a component of those platforms. And so this leads me to divide Earth's climate system into three broad states. One in the Precambrian, where carbonate sedimentation was more kinetically inhibited than in the Phanerozoic. One across the Paleozoic, where the carbonate rock reservoir was being built on cratons, and biomineralizers really drove a long-term cooling. And then this third state, after we evolved planktonic organisms to change how the carbonate was recycled back into the solid earth. And so I'll leave the conclusions, but I'll say that this model then predicts that tectonic forces, changes in oxygenation, are all higher amplitude effects on this long-term change in the climate states over Earth's history. So, thank you.